Hi, everyone. Thanks for coming to the DGRAV seminar series. My name is Delilah. I'm a postdoc at Princeton and one of the organizing members for this seminar series. Thank you so much for joining us. Just for those who may not have joined us last time, this is our second of such in this series of seminars. And the idea behind this seminar is to have some talks that are joint between two people, a more senior scientist and a more junior scientist, where for the first 15 minutes, we have a presentation by our more senior scientist to kind of give us an overview and bring us all into the realm of what we're going to be talking about. And then a longer session about 30 minutes where the more junior scientist will go into details about the work that's being presented. Today, we have for you a talk on searching for ultralight particles with black hole superradiance. Our first speaker is going to be Professor Asimina excuse me for the pronunciation, Arvanitaki. She is the Stavros Niarchos Foundation Aristotelos Chair at the Theoretical Physics in Theoretical Physics at the Perimeter Institute for Theoretical Physics. She was given a New Horizon in Physics Prize in 2017. Before that, she did postdoctoral studies at Stanford, and her work draws on ideas from the Standard Model and precision collider physics, as well as combining that with experimental techniques from other fields to develop novel ways to experimentally test for otherwise inaccessible phenomena that can get at the heart of questions like, what is the nature of dark matter, or why is gravity so weak? Our second speaker is going to be Masha Baryakhtar. She's an assistant professor in physics at Washington University, before which she was a postdoctoral fellow at Perimeter, and before that, a postdoctoral fellow at New York University. She did her PhD studies in Stanford, finishing in 2015, and she studies beyond the Standard Model theories, searching especially for light dark matter candidates, as well as ultralight particles using black holes and gravitational waves. Thank you so much, you all, for joining me, and I will turn it over to you, Mina, to start.
Thank you, Delilah. Thank you. So for the next few minutes, I will try to give you a brief introduction as to, let's see if that works. Okay, that works. How black holes can be probes of ultralight particles, in particular bosons. And the characteristic we will rely on is the fact that black holes have a characteristic size set by their horizon size, which for astrophysical black holes is anywhere between 1 kilometer and 10 billion kilometers, as many of you know better than I do. And the point is that the effect of black hole superradiance affects their evolution and makes them sensitive to the presence in the theory, not necessarily in the universe, just the fact that they are present, that you have these extra particles in the theory, and they the presence of these particles has signatures and can tell us whether or not they're there. Now, before I tell you exactly what black hole superradiance is, I will give you a motivation about why looking for this type of particle is a good thing. And one such ultralight boson goes by the name of the QCD axion. And this is perhaps the most famous ultralight boson that we know of. So in the Standard Model, one can write a term that effectively mixes the electric field of the strong interactions and the magnetic field of the strong interactions. So it mixes a CP odd with a CP even quantity. And this is, so it violates charge and parity symmetry at the same time. The strength of this term is parameterized by the theta parameter, what we call the theta parameter. And we expect this parameter to be order 1. Now, if this parameter was order 1, it would produce a fundamental electric dipole moment for the neutron, basically a charge asymmetry. And we have looked for it for actually quite a bit of time. And the only thing we've managed to do is only constrain this theta parameter to be less than 1 part in 10 to the 10. This has been a moment, as I said, this is the status of the experimental searches right now, but this has been a problem for decades. And back in the 70s and 80s, people proposed that this is a naturalist problem, as we call it in particle physics. And as a solution, people proposed that this theta parameter is a dynamical field, and they called it the axion. The cosmological evolution of this field, of this axion, naturally relaxes this theta parameter to 0. So you wouldn't expect to find an electric time moment for the neutron. Now, the axion gets its mass from non-perturbative effects in QCD. And as I've advertised, its mass, its produced mass, is much lighter than any of the norm scales of the standard model. In fact, it can be more than 20 orders of magnitude lighter than the mass of the proton. So its properties are uniquely characterized by the axion decay constant. And if this axion decay constant is close to the Planck scale or the GATT scale, you find that the Compton wavelength of this axion is roughly 3 kilometers, which matches the size of stellar mass black holes. So this particle now is an excellent dark matter candidate. And there are several experiments looking for it. So now this is a great example of how astrophysical searches can connect with laboratory searches. Now, if one goes to even bigger extensions of the standard model, like string theory, we find that the axion does not come alone. It actually comes with cousins. And in theories like string theory, this happens because there are 3 ingredients that you need. First of all, you need the theory to have extra dimensions, more than the 3 that we observe, to make the theory mathematically consistent. There are gauge fields, there are particles that live in these extra dimensions. And there's topology. We know, of course, we don't live in 10 dimensions, we live in 3. So the extra dimensions need to be made small. Now, topology is essentially the shape with which we compactify these extra dimensions. So we can simply compactify them on a sphere or on a torus, or in fact, the only thing that limits us is our imaginations and what we know about geometry. So it turns out, combining these 3 ingredients, taking these extra dimensions, compactifying them in complex ways, and having gauge fields that live in these extra dimensions, can produce particles that manifest themselves in our universe, in the 3D universe that we live in, as extremely light cousins of the QCD axion. Okay, and we call these axions string axions, or sometimes you will call them ALPS, axion-like particles, because there is only one axion in the minds of many people. So now there is another class besides the axions, and it goes beyond a bit. So with the same ingredients also give rise to spin-1 particles. What is known as sometimes, and this is something that Masha will talk about quite a bit, they are known as dark photons, and they are actually cousins of the ordinary photon. They just couple to us extremely weakly. Now, there is another class of bosons that have slightly different properties than axions and dark photons. They go by the name of dilatons, moduli, and the radion, and they are the ones that are responsible for setting the shape of the extra dimensions, as well as the values of the fundamental constants that we measure in our universe. Okay, so the takeaway message from this is that we have good theoretical motivation, either from naturalist arguments or from looking at the bigger frameworks than the standard model, to expect that there are these very light particles in our theory. Now the question is, how do they manifest themselves? So the way, and I should say all of these particles are excellent dark matter candidates. And in fact, we have tons of experiments that look for them in a laboratory setting, if they are the dark matter. So axions, if they are the dark matter, can convert to photons in the presence of of magnetic field, or they can make spins precess if they are the dark matter. Dark photons couple similar to the ordinary photon, and they can mix with it. So anything that can detect ordinary photons will be automatically sensitive to these dark photons. And lastly, these other scalars, these moduli that determine the shape of these extra dimensions that I mentioned, they will cause variation, local variation of the fundamental constants, in fact, oscillations that you can detect with atomic clocks. Okay. Now these are the signatures assuming these particles are the dark matter, and as I said, they are excellent dark matter candidates. But there are signatures that are independent of what happens in cosmology, what happens in the history of the universe. So whether or not we produce them in the universe, we don't care about it. So people can design experiments to look for them. For example, axions, and as well as dark photons, they can mediate new forces between matter. So you can do a force experiment. And this is, in fact, and of course, there is also experiments you may have heard look for axions called light shining through wall experiments that I won't go into details for them. But the important thing from here is that black hole superradiance falls in this category. So it's a probe of particles, of bosons, ultralight bosons, independent of their cosmological history. And of course, because we're talking about black holes, and we're talking about the force of gravity, which is universal for everything, in some ways, it's even more powerful than all experimental probes because it only cares about the universal force of gravity. Okay. So what is superradiance now? So superradiance is not special to gravity. In fact, it can be observed in a variety of systems. So a very simplified cartoon of what superradiance is the following. So let's imagine we have a cylinder that is rotating. And let's take a ball and scatter it tangentially from the cylinder. If at the point of contact, the cylinder is moving more slowly than the ball, friction will cause the ball to slow down. Now, let's speed up the cylinder, and at some point, when the cylinder becomes faster than the ball, friction will cause you to grab onto the ball and give it a push, transferring energy from the cylinder to the ball. So this is a process where friction kind of gives away energy instead of taking it away. A similar thing can happen with waves. And in fact, some of the first versions of superradiance were worked out for not for gravitational waves, but for electromagnetic waves. Here, so you have a rotating cylinder, and instead of friction here for a wave, for an electromagnetic wave, friction for electromagnetic wave is dissipation, which means finite resistivity. Okay, so you have some conducting cylinder. So if you have a conducting cylinder that rotates and its angular velocity is larger than the angular velocity of the wave, what will happen is the wave will scatter from the cylinder and will come out amplified. And this is something that has been worked out by Zeldovich back in the 70s and many people, and there's a very nice paper by Bekenstein from the 90s that describes all this. Now we have black holes. Black holes intrinsically have dissipation or friction, and that comes because they have a horizon. Whatever you throw in the horizon, in fact, is the perfect absorber. So whatever you throw, you have to have things falling in. You cannot easily have stuff. You cannot have stuff coming out. So what will happen here? Let's take an electromagnetic wave or a gravitational wave. And what will happen is, if the black hole is rotating faster than the angular velocity of the wave will come out amplified. Okay, so this is a process that extracts energy and angular momentum from the black hole. Now, Back in the 70s, where most of this stuff were worked out, Press and Topolsky made the following thought experiment that said, okay, let me take now this black hole and my electromagnetic wave and surround the whole system with a perfectly spherical mirror. And I performed the same experiment. Now, with every reflection, the wave gets amplified by an amount that's proportional to the previous amplitude. So the amplification is exponential. Eventually, radiation pressure becomes so large that it makes the mirror explode. So he called this the black hole bomb. Now, the question is, of course, this is not in any case a realistic situation, but the key point to this was that the electromagnetic wave is made out of photons, which are bosons. So if you have massive bosons now, instead of a photon, what will happen is the mass of the boson allows you to create a bound state with a black hole. In the case of the photon, that's not possible. You have the wave, it comes in, it scatters and goes back to infinity. But if you have a massive particle, it can create a bound orbit with a black hole. And its mass acts like a mirror that confines it to the vicinity of the black hole. So what you will see happen, and again, this is optimal where the massive boson Compton wavelength matches the size of the black hole. It's close to the size of the black hole. What you will see happening is the black hole spin down, and a cloud of these massive bosons will start occupying, grow exponentially, occupying a bound state around the black hole. Okay. And as I said, the physics of this is known, the mathematics of this has been worked out beautifully by Amour, Zouros, Detwiller, and others back in the 70s and 80s. What we realized more recently is that this can happen, is a viable process for astrophysical black holes. Now, Masha will go into many details about the dynamics and the evolution of the system, but I will guide to give you a bit more intuition about how to think about the system. So now, how do these orbits look like? Now, unless you sit very close to the black hole, the potential that the particles, the boson sees, is a 1/r potential. So if you were to solve for the bound states of the Klein-Gordon equation, what you will find is that you have quantized levels. And those levels have characteristic quantum numbers. They have the orbital quantum number, the principal quantum number, and the magnetic quantum number. There is the analog of the fine structure constant, this parameter alpha, that tells you how strongly the boson couples to the black hole. So it's like a gravitational atom in the sky. Now, there are very important differences, though, between what you have here as a gravitational atom and the ordinary atom, the hydrogen atom. First of all, there is, of course, the size. We're talking about atoms that have kilometers or billions of kilometers in size. But the other thing that happens is you have bosons instead of fermions, like the electron, occupying the bound states. So that means that the occupation number can be ginormous. In fact, you can have more particles in those bound states that you have protons in all of the stars in the universe. Another very important thing here is that I said that the energy is quantized. Now, there's another characteristic thing for the energy of these bound states in the gravitational atom around the black hole is that the energy has a small imaginary part. And that happens because you need to put in ingoing boundary conditions at the horizon. In the hydrogen atom, there is no horizon, so you just require that the wave function is regular at the origin. So this crucial difference converts what you thought was a Hermitian problem to a non-Hermitian problem. So what you find, as I said, is that there is a small imaginary part in the energy, in the binding energy, and this is where the superradiance effect comes from. Now, the imaginary part leads to this exponential growth that I talked about before, and that happens when when this inequality is satisfied, which is essentially what I told you, that the angular velocity of the particle, of the boson around the black hole, is less than the angular velocity of the black hole itself. And the other thing that's relevant is that this instability, this exponential growth, can happen fast compared to the known timescales of the evolution of astrophysical black hole. That is the black hole accretion rate. So for stellar mass black holes, for example, this superradiance instability can happen as fast as 100 seconds. And as Masha will talk about, for spin-1 particles, this rate is even faster. So for stellar mass black holes, the superradiance instability can happen as fast as 1 second. Okay. So there are several things. There are many signatures of this, if that occurs in our universe. First of all, because the growth of the cloud takes out energy and angular momentum of the black hole, the first thing you would expect to see is not many rapidly rotating black holes. And in fact, observations of rapidly rotating black holes can be used to constrain the presence of these particles. Now, and this is something that Masha will talk about a lot, these bosons are actually their own antiparticles for axions and for spin-1 particles. So they can annihilate and produce monochromatic gravitational waves that give signals in LIGO and LISA. And this is, as I said, this only depends on the force of gravity and whether or not you have a particle in the right mass range to affect the evolution of astrophysical black holes. There are also signatures that depend on couplings other than gravity. So, for example, if the boson is an axion and has self-interactions, you can have scalar wave emission, and those scalar waves can be looked for experiments that look for dark matter axions. Perhaps the most exciting thing is something new that Masha and her collaborators discovered recently, that in the case of dark photons, if you have couplings with the environment, this coupling can inject a lot of energy in the environment of the black hole and can lead to very interesting electromagnetic signatures. But I don't want to say any words about how they call it because I will steal Masha's thunder. So with this, thank you, and pass it away to Masha. If you have any questions, I'll be happy to take them now.
Thank you so much. I think since you've done a great job of introducing us all to this and previewing what Masha is going to talk about, we're all excited to hear what she has to say to us. So if I can ask everyone to hold their questions, either type them in the chat and I'll ask them at the end, or you can hold on to them yourselves and you are welcome to ask our speakers at the end. But why don't we let Masha take us away?
All right, let me just share my screen. Every time I do this, I'm still nervous after having done it 100 times if it's gonna work. No, it's paused. Resume. Okay, 1 second. Okay, maybe I'll make it full screen first. Okay. Can you guys see that?
Yes.
Okay. Oops. Well, I didn't see. Oh, there we go. There's my title slide. Does it appear okay? Okay. Excellent.
Yes, it does.
Great. All right. Well, thanks so much for having us, and thanks, Mina, for the great introduction. So, as Mina was saying, today I'll talk about some of the signatures that you can get from this superradiance process around rotating black holes. And so what we've learned so far is that you have a huge amount of energy that's extracted from a rotating black hole if you have these new ultralight particles. This is a simulation of a cloud of spin-1 particles around such a black hole. And the density in these clouds is huge. It can be comparable to the matter density of a neutron star. So it shouldn't be surprising to you that you can use this process to observe that these phenomena should be observable, that this can lead to some pretty dramatic signatures, and there will be signatures across different types of spectra, both gravitational waves and electromagnetic waves. So I'll spend the rest of the time we have today talking about 3 main points. One is the gravitational signals of new bosons, building on what Nina was already talking about. And then I'll talk about some new work, which is looking at superradiance of particles that are not just gravitationally interacting, but have some mixing, as we call it, with the standard model particles. And we'll see that this gives us some dramatic signatures, which we're calling a new type of pulsar, which can give rise to multi-messenger searches for new physics. So Mina talked about these gravitational atoms. I wanted to introduce you to gravitational atoms for spin 1 particles. So this was work I did a few years ago with May and Robert, figuring out how these gravitational atoms behave if the so-called electron in the atom, in this case, it's the boson, has a spin 1 intrinsic spin. So unlike the axion, which is a scalar, the dark photon, which is another of these new light particles that you can have in theories beyond the standard model, has spin 1, just like our photon. And so the bound states it forms around gravitational atoms look a bit different, but you can kind of picture already from what I was saying is that you can think of these as just particles that have a spin along with the quantum numbers that Nina described for the gravitational atoms, which are the total orbital angular momentum, similar to how the electron has a spin quantum number and the total angular quantum number. So this is a picture of what bound state of the dark photon around a black hole would look like. And just to compare it to between scalars and spin 1, which are spin 0 and spin 1 particles, in the top row, I'm showing the energy density of bound states of scalar. So these are labeled by the principal and orbital quantum numbers. So the first one on the left here is the S. Can you see my pointer? Okay. The first one on the left here is the spin 0 state, the S wave, which doesn't superradiate because it can't extract any of the rotational energy. And then you have the fastest growing rate one here, which has spin 1 and so on. For dark photons, you have the same similar energy density distribution, but now you have this extra quantum number, which is a spin, which allows you to make a S wave orbital for the dark photon bound state around the black hole, which has 0 orbital angular momentum, but it still has a total angular momentum number J of 1 because the photon itself carries a spin. So that means that you can have these states that sit very close to the black hole compared to the p orbitals, which are pushed a bit farther away from the black hole. And we'll see that that makes faster rates and bigger densities. And everything is rotating around the black hole. So let's talk through how this growth happens. So the black hole, if it's formed with high spin, the black hole spins down. And what happens is that the fastest growing level is formed. Here I'm talking about spin 0 particles. So on the left, I'm showing the parameter space for black hole spin versus mass. The blue regions are where superradiance is active, so the black hole is spinning fast enough compared to the angular velocity of the particles in these levels that they can extract the black hole's energy. And on the right-hand side, I'm showing the number of axions as a function of time and the black hole spin as a function of time. So you can see in just about a year, once the black hole is born, if it has an initially high spin, like in a LIGO merger, then it'll drop down fairly quickly by producing this huge number of axions. At parametrically longer times, you will form the next level, which has higher angular momentum, so it has a bigger angular momentum barrier. localizing most of the particles further away from the black hole, which cause the rates to be slower. They have less overlap with the region where they can extract the angular momentum. And so the next level, which is through the 322 level, grows at parametrically longer times, and the black hole takes another jump in the spin, where it dumps a lot of its spin to these particles. In between, what you have is gravitational wave emission. So as Mina alluded to, these particles don't have any conserved quantum numbers. And in fact, you can just think of this as a giant rotating quadrupole energy density that you've set up because of the intrinsic angular momentum of these particles. And so it's going to radiate gravitational waves very efficiently at frequencies of twice the mass of the particle, which is the rotation frequency of this cloud. And that's going to cause the number of axions in the cloud to deplete over time. The main difference between this scenario and what happens if the particle has a spin 1 is, as I mentioned, you can have in this pink region here, this pink cloud here can be localized much closer to the black hole than the blue cloud, which is for axions because it has a lower angular momentum, lower orbital angular momentum. So that means that all the rates are faster. So on the right here, I'm showing a plot of the rates as a function of this alpha parameter, which is how tightly bound the particles are to the black hole gravitationally. And on the right-hand side, you see the time scales in seconds for the growth of this cloud. So as Mina was saying, these can be quite fast. For the vector, which is shown in green, the time to increase the cloud by a factor of 2 in size is of order seconds or hundreds of seconds. For scalars, it's parametrically slower, so hundreds of seconds to thousands of seconds. And it depends on what the mass of the black hole is relative to the mass of the particle that we're looking for here. I fixed a particular particle mass, and you see if the black hole mass gets lighter, the overall rates get slower. And so within the same time, you can spin down the black hole to much lower values of the spin if you have a spin 1 particle rather than a spin 0 particle. And I'm not sure what the policy is on questions, but I'm very happy to take them throughout, because if someone is getting lost or confused, I'd rather know now than at the end. So please feel free to ask. So that's the black hole grabbing the dark photon cloud or the axion cloud. And as I mentioned, there's this depletion of the cloud into gravitational waves. And luckily for us, we know how to observe those now. We have these very exciting discoveries, and we are quite sensitive to very weak signals of gravitational waves. These types of gravitational waves are different from the big black hole or neutron star mergers that we've all heard about. Probably many of you are also familiar with this class of searches. This falls into the class of what's called continuous wave gravitational wave searches, which are mostly focusing on looking for rotating neutron stars that are not perfectly axisymmetric. So maybe they're a little squished on one side, or they have a little bump. And those emit very close to monochromatic gravitational waves for a very, very long time. And that's very similar to what's happening here. You have this cloud that's rotating, and it's very slowly depleting into these coherent gravitational waves, which are set now not by some arbitrary initial conditions of how the neutron star is rotating, but by the mass of the new particle. So if you see these, if you see some of these signals, you expect all of them to be very close in frequency, which would be quite interesting. And these searches are currently being done. So just to give you a sense of what's possible, if you look for these signals from rapidly rotating black holes, the reach of the projected Advanced LIGO Virgo detectors at their design sensitivity will be able to see gravitational waves from dark photon superradiance as far as 1,000 or a few thousand megaparsecs. For axions, the reach is a bit lower because the cloud is more diffuse. And there's, so the power in gravitational waves is lower. And what I'm showing in the dashed lines here are what the reach could be for a search that follows up the first black hole mergers, the 150914. So if that black hole had an axion or dark photon cloud around it, and then we looked at the follow-up continuous wave signal that's coming from the cloud afterwards, we should be able to see it. And that's something that I know the people are working on for upcoming observation runs.
Okay, excuse me, can I interrupt you for a second for a
Yes,
question?
please.
Okay, I'm sorry, but somehow the concept that you're putting forward, dark matter, radiating photons, there seems to be a little bit of oxymoron there. If dark matter emits photons, it's not dark. Well,
so far,
we can
let
see
me
it.
let me just quickly stop you there. So far, I haven't said anything either about dark matter or about it radiating photons. So just to be clear, as Mina was emphasizing at the beginning, this is not dark matter. These are new particles that are produced from the rotational energy of the black hole. You're right that they are good dark matter candidates. So that's, but so we're not assuming anything about it being dark matter. And so
Okay.
far, I'm just talking about them producing gravitational waves. So far, we're just discussing how they are could be detected through purely gravitational means, which is very interesting because as you point out, we want to get at the gravitational coupling of these particles.
Okay, I'll just take the word dark photon to have an ambiguous meaning at the moment.
Yes,
So I can go
dark
forward with
photon. Yes, dark photon is a bit of an oxymoron, but basically we mean a new particle which has properties similar to our photon in that it has a spin 1 and it carries it's a
energy.
gauge field, but it is dark, so its coupling is much weaker than that of the photon. Yeah, exactly.
Okay, thank you. One more question, if I can, please.
Yeah.
I understand gravity, that is gravitational waves, have spin 2.
Yes.
And therefore, I'm a little bit troubled by your designation of principal quantum numbers in regard to the I'll say the motions of the orbital properties of the of these particles that you're saying are being emitted. You started out with principal quantum numbers, etc. I think I understand what I'll call the spins of these things and the angular momentum, but I don't understand how you assign quantum numbers that are not equal, because the transition from one quantum state to another requires that the delta, the change in the principal quantum number be
I
2.
think I understand your question. Yeah, exactly. Very good. Right. So maybe this picture actually is a useful one here. So these states are produced with any quantum, with the series of quantum numbers. So let's focus on the fastest one, which has quantum number 1. It has angular momentum 1. And so you're right that to have to produce a gravitational wave without additional suppression, you need 2 of these particles. So you're thinking of a transition from one level to another, but these particles can actually come together and annihilate. So you take 2 spin 1 particles and you make 1 spin 2 particle.
Oh, okay. I'll keep that in mind. Thank you.
Great. Yeah, very good questions. Okay. So we can look for these gravitons that are being produced as follow-up searches, and we expect that at current and especially potentially future gravitational wave observatories. Here on the left, I'm showing us axion, and on the right, I'm showing a dark photon, which is proxy for spin 0 and spin 1 bosons. The expected events per year that you could see are of a merger that say Lagerberger observes, and then you do a follow-up search for these continuous gravitational waves, and you know what the mass is of the black hole that formed, you know the spin of the black hole that's formed, so you can predict the waveform pretty well, and you can see potentially many of such events, which would be a real smoking gun of this kind of process. So this is just a quick summary of some things you can do. There's a huge range of work that's being done right now on this topic, which is super exciting. So there's searches for follow-ups, there's blind searches for these signals coming from different black holes in our galaxies. There's searches for the stochastic sum of these signals over different bands. So I definitely, if you're interested in this, I'd love to talk more offline. I think there's a lot of exciting stuff going on, and there's prospects for, you know, a real discovery here, which would be very cool. So that concludes the gravitational part of my talk, and I want to move on to some new work, which is on superradiance. When we tried to connect these particles to the particles we already know exist. So this is a parameter plot of these dark photons. The x-axis is the mass of the dark photon in electron volts. So the electron is up here. And this is a coupling constant or mixing parameter epsilon. So as you go up, you have larger interactions with the standard model particles. So far, we've been doing discussions all the way down here, which are at very low coupling. Basically, we're assuming there's no coupling to the standard model. We're just relying on gravity itself. And you can see that there's a lot of activity and interesting searches that are being done in this parameter space. So the gray regions are things that are already excluded without assuming that this particle is the dark matter, just from other tests like what Mina was mentioning. So the question is, what happens to the superradiance if you have this coupling, which in principle is quite generic in theories beyond the standard model. So this is what's called, so this is the region we're interested in, and these types of couplings were first written down in the 80s. Basically, we have a Lagrangian, which is very similar to what you're used to from electromagnetism, F mu nu squared, but then you have a mass term for this photon, and then you have this epsilon, which is a kinetic mixing between our photon, which is not primed here, and the dark photon, which has a prime. So this is the new terms that you add to the theory, and this can be generated by any couplings at any particles at any scale that are charged under both these gauge groups. So this epsilon can be generated quite easily, and it's called the kinetic mixing parameter. And the effects of this parameter are that the dark photon, which gives rise to dark electromagnetic fields, just like as our photon gives rise to regular electromagnetic fields. The dark electromagnetic fields, in the presence of this kinetic mixing parameter, can actually couple to our electrons, albeit a suppressed charge. So this charge could not be order 1, otherwise we would have seen it already, but it can be as big as 1 part in a million without already having been constrained. And that can be generated, say, at 2-loop level in a field theory. So we're going to look at the effects of these types of particles. And this is work with some outstanding collaborators at Perimeter Institute, which we're hoping to wrap up in the next month or so, mostly led by Niels Simonsen, who's been doing all of the hard work doing the doing and understanding, which is non-trivial, the simulations of these effects. So superradiance sets up what we're going to see is superradiance sets up these dark electromagnetic fields. As I said, they have density that's close to neutron star matter density. So the energy stored in these dark electromagnetic fields is as big as the matter density of a neutron star. And so even if there's a very small mixing parameter between these dark electromagnetic fields and the matter that we're made of or is out there in the universe, then there can be some dramatic consequences. So let's go through this step by step. What happens first? The black hole generates a dark photon cloud, as we said. It looks like this. I'll call the dark photon A prime. In the usual way, you can calculate the electric and magnetic fields from a vector potential. And these dark fields, primed fields, to our electrons look like a small parameter multiplying this dark field. So basically, you can just think of them as electromagnetic fields, but suppressed by a small parameter. To give you a sense of the numbers, the amplitude of the fields is of the electric field is about, for the particle physicists, 10 keV squared. For the astronomers, it's 10 to the 10 Gauss, which is on the order of pretty strong magnetars. And this depends on this new physics parameter epsilon and alpha, which is the gravitational coupling constant between the dark photon and the black hole. And it's mostly dominated by the electric field rather than the magnetic field. So the magnetic field is suppressed by a factor of alpha, which is less than 1. The size of this cloud can be about hundreds of kilometers. And that means that these electric fields can accelerate electrons to very, very high energies. So the electron going from one side of the cloud to another, the potential difference is 10 to the 10 GeV. So these can be accelerated to very high energies. So what does that mean? You have an electron. Let's assume that the black hole was just formed in a black hole merger in a fairly clean environment. There's not a lot of stuff around. Even in that case, there's going to be some electrons in the environment of the black hole. As the cloud grows, the electrons in the black hole neighborhood will get accelerated to relativistic speeds. And this whole time, the electric field around the black hole is turning at the frequency that's set by the mass of the particle, because those are the solutions for these spin 1 fields. So as the field is turning, the electron will curve and radiate high energy photons. Once these photons are emitted, if the field is big enough and the electrons are moving fast enough, they will encounter the background field and cause a cascade, which leads to runaway particle production. So you have single electron emit a photon. That photon interacts with a large background electric field, which is known as assisted Schwinger pair production, to create 2 more electrons, or electron and a positron rather. And there's other nonlinear processes that occur as well. And these are not unique to this scenario. These happen in other extreme astrophysical environments where you have large electromagnetic fields. So you have a run. Yeah.
Sorry, can I ask you a question?
Yeah.
I'm not sure if I'm supposed to ask questions, but anyway, does it depend on what the background density of electrons is? Does it matter, like the initial
so
density?
here, so there are some things that matter. So here I'm just assuming that you're starting, the final density is the one that's generated by the electromagnetic field. And that's pretty large. That's larger than the ambient density, but it's smaller than, say, the density of an accretion disk. So for now, I'm just talking about most of the plasma that's generated is not initially there.
Okay, thank you.
Yeah. Okay, so this is what I said before. So you have these electrons, they produce more and more electrons in an exponential cascade. Eventually, you produce enough charged particles that they start to screen the electric field that's produced by this cloud around the black hole. Set up a dipole, which is trying to cancel out the visible component of this dark electromagnetic field. And this dipole is trying to rotate along with the electric field to continue canceling it out. So now we have this large amount of plasma density and this rotating dipole that's been established, which happens, oh, and here, let me show you the actual simulation of this. So this is showing you the positive and negative charges that are rotating in the equatorial plane around the black hole. So this is very beautiful. The cloud here is for about this big and starts falling off exponentially at larger distances. So the three steps are: the black hole is generating a dark photon cloud. There's a runaway cascade of charged particles, which creates a rotating dipole. And then you have a large amount of rotating plasma and electromagnetic fields, which will produce electromagnetic emission. And that then we hope to observe. The regions of parameter space where this is relevant are shown here. So for those of you who are familiar with these dark photon parameter space, you can see that you in regions which are currently not constrained by any other experiment, the orange curves show when these charges start to accelerate rapidly within these fields for two different mass black holes, and the red regions are when you have this runaway cascade. So this is where you get this formation of these rotating large charge densities. Yeah, Amina's question, it is possible to extend this parameter space if there's existing charge density already surrounding the black hole, which is good and bad. It can be a bit more messy, but and it doesn't, you don't expect it to appear around, say, a LIGO merger, but it can be interesting to also consider situations where you have existing charge density, which would produce this effect without it having to be generated by the cloud itself. So now we have these huge electromagnetic fields along with a plasma that's trying to track them, which sounds kind of familiar. And if you've thought about pulsars, you have these big magnetic fields with some charge density around it, which produce radio and X-ray and gamma ray emissions. So we did simulations to try to understand how big the power is that you emit and how much and what its characteristics are. So I'll just summarize that briefly here in the interest of time. So the really interesting thing that we found in the system is that basically the fields close to the black hole are sourced by this black hole solution. So they're locked and they're locked in this rotation at the frequency given by the particle mass. So close to the black hole, the fields themselves, so here on the left, I'm showing the magnetic field, are rotating at a frequency given by the particle mass, so say a kilohertz. The charge density is tracking the electric field and canceling it out. As you go further from the black hole, it becomes impossible for the plasma to keep up with the electromagnetic fields because the far away, they're rotating faster than the speed of light, so the plasma can't keep up, and you have differential rotation that's established. You also have dissipation in the plasma because of high energy processes that are not included in the simulation, but we know happen. For example, losses due to curved trajectories and photon emission pair creation things I've already mentioned. So the combination of this differential rotation and these dissipation mechanisms give rise to this turbulent behavior in the field. So you have these small scale structures appearing in the magnetic fields and in the plasma, which are very cool and very pretty, but also lead to large amounts of dissipation on short scales. So basically all of these electromagnetic fields are dumping energy into these turbulent swirls of plasma. This is a plot of the power emission here at a fixed time. So you can see that the total power that's dissipated has a very non-smooth structure. So you have these areas of high emission of power and low emission of power, and these evolve over time. And this is mostly dissipative power, so it's not coherent radiation. Initially, we thought that this rotating dipole would emit kind of coherent radiation because of dipole radiation to large distances. But then Niels found that most of the power is actually dumped into the plasma because of these turbulent processes. And so that gives rise to actually higher energy emissions like X-rays and gamma rays. Oops. So this is the luminosity that we expect. So as a function of this parameter alpha, which you can think of as being proportional to the mass of the new particle, there's two types of emission. There's in orange is the resistive emission, and in blue is the kind of coherent electromagnetic flux that just escapes the cloud. So because of the dense plasma and the short scale features, most of the energy gets dumped into these higher energy processes, and that power can be huge. So as high as 10 to the 44 ergs for epsilon 10 to minus 4, which is about a factor of 10 to the 5 or 6 larger than the crab pulsar luminosity, and even another factor of a million brighter than our sun. So these are super bright objects, and so these are kind of anomalously bright pulsars because the energy density in the cloud is large, and its extent, the electromagnetic fields that are carried by it are extend to very large distances from the black hole. So we also think that these can be similar to pulsars. The emission can be periodic. So this is showing the dissipation as a function of time. The top 3 plots are showing the energy dissipated screenshots corresponding to 3 different times here, where this is for different values of the particle mass. So you can see there are some characteristic structure similar to that of a pulsar that you could try to look for in observations. So in the last couple minutes, I'd just like to give you a sense of the types of signals that you could hope to see with this. So you, let me skip this. So there's 2 classes of searches that we're currently investigating. One is electromagnetic follow-ups to black hole merger events. So a black hole, similar to the gravitational wave follow-ups, if you have a merger, you make a new fast spinning black hole, then you create these pulsars in quotation marks in a matter of hours or days, and then the signal decays slowly over time. Another interesting idea is kind of the reverse process. So if you already see something that looks like a pulsar, but it's a bit weird, it could instead be a black hole superradiance in disguise. And by a bit weird, I mean that the pulsar is spinning up. So usually when pulsar spins down, it loses energy. But if in this case, the frequency of the rotation actually goes up a little bit because the gravitational binding energy of the cloud is decreasing over time, which allows for faster rotation around the black hole. So we can look for spin up pulsars and then try to follow those up with gravitational wave observations. So here are some projections. So if you look at some existing black holes that were created in a merger, and then follow them up with an observatory like Chandra, for example, you could have sensitivity above these solid lines. The shaded background regions are where this cascade happens. So you have enough plasma to source this luminosity. And these are the gravitational wave strains for a catalog of 64 pulsars that have been observed to have positive F dot. You can see that most of them lie above the LIGO sensitivity, unlike what would be the case if these were actually rotating neutron stars. So typically you would say you wouldn't be interested in following these up because it's so unlikely that you'll see them in a gravitational wave search. But if they're coming from superradiance, then they would actually be above your sensitivity and they would be worth pursuing. So I'm over time, sorry about that. So let me just conclude. So I talked about how rotating black holes will produce clouds of these weakly coupled bosons through superradiance. And in the case of dark photons, if they have a standard model mixing, will lead to some dynamics around the black hole and perhaps give rise to a new class of pulsar-like objects. So thank you very much.
Thank you so much, Masha, and also Mina. So we are over time, so if there, but we can take a few questions before we adjourn. So if there's anyone who has to go, who has a pressing question, maybe I should let them start. If not, feel free to anyone raise your hands and I can call on anyone to ask questions. So does anyone have any urgent questions?
Can you hear me?
If not, maybe, yes.
Oh, excuse me. I kind of have the impression that a lot of the information that you are presenting is theoretical in nature. And I wonder if you have any actual observations or data that kind of that you can put on these graphs, on these plots, so that I could get a feeling for, well, I'll say something that's different than what you're proposing.
So there's kind of two aspects to your question. So there's, the things we're proposing are by definition not yet observed because we're trying to look for new particles, which are theorized to exist because of the motivation that Mina discussed at the beginning. But so far we have not detected them, and this would be a new way to detect those particles.
Okay.
But some of the processes I'm discussing some of the aspects of the processes have been cross-checked with other observations. In particular, we're relying a lot on the observations and modeling techniques that people use for pulsars, which obviously we know exist in magnetars. So some of these dynamics, in a sense, have been observed, and that's kind of gives us confidence that some of these claims we're making are correct.
Okay, thank you. And then there's one other question I had in regard to, you talked about this cloud of, I'll just say particles of some kind that are clustered around, and how that cloud actually was formed by the strong interactions of the fields that were involved. And it seemed like I heard you allude to what I'll call the angular momentum of this cloud. And I'm under the impression that gravitational and electromagnetic fields, at least, conserve angular momentum. And since there was none there to start with, I can't quite picture how you're all of a sudden starting it rotating, because just formed in a
The angular
area.
momentum,
Yeah.
so this is good to emphasize. So the flow of angular momentum is as follows. You start with a black hole that's rotating.
Okay.
And then what happens is you're actually slowing down the rotation of the black hole, and that angular momentum difference is what is ending up in the angular momentum of the cloud.
In your cloud, yes.
And then the cloud is sourcing either gravitational wave or electromagnetic radiation, and those carry away some angular momentum, thereby depleting the cloud itself. So over time, the cloud will disappear.
Well, over time, I think because of the mechanism you're proposing, the black hole itself would slow down its rotation.
Exactly. Yes. Absolutely.
And that being the case, I would expect that most of the black holes that you might observe, which are not necessarily recently formed, would not be rotating.
That's correct. Yep, that's right.
Okay, thanks. I'm just trying to, work through this. This is the first time I've heard these things. And, and I'm trying
in fact, I mean, Masha showed, I mean, you can go back to some of your plots. Masha showed some gray bands that are actually constrained from spin measurements. So the fact that we have seen some black holes, especially in X-ray binaries, that are fastly rotating, and we know something about the age of the system, puts constraints on these particles.
Yeah, exactly. In interest of time, I didn't discuss those, but here's an example. I can quickly flash here. So here are constraints, and for some of these particles, which we've placed, these are for axions, using measurements of rapidly spinning black holes from X-ray binaries as a function of particle mass and interaction. So you can see that these measurements saying that these black holes have spin of, say, 0.95. By this time, they would have definitely been spun down by this process. So you can exclude this range, but these bounds kind of peter out at stronger couplings of these particles. Yeah.
So it's kind of like a pulsar. When they're spin down, I'll say they radiate energy, and therefore their periods become longer and longer. And
so here it's like a two-step process. So first you make the cloud, and then you deplete the cloud. The pulsar is just directly radiating.
And so you're kind of looking at the age of the black hole or the pulsar. When it spins down, it loses its angular momentum, and so the older black holes, for instance, would tend to be low spin or not spin at all.
Yep.
Okay.
Well, there is a limit actually to how much spin you can extract.
I see.
So radiance.
So you would here, if you look at this figure, you would expect all the black holes to kind of lie along the bottoms of these curves.
In the interest of making sure anyone else who has questions, sorry to interrupt real quickly. I just want to make sure if anyone else had some questions they wanted to jump in. This is very interesting discussion. But I just want to make sure if anyone else has pressing questions. Yes, please.
Hi, Masha. It's Ted.
Hi, Ted.
You might have said this and I just missed it, but what are the observational constraints on this epsilon parameter that governs the coupling of the dark photon to the photon?
Yeah.
I mean, not just what they are numerically, but what's the nature of them? I'm kind of surprised that it could be as large as you're considering.
Yeah. So it's actually interesting. So this is the summary here. There's a range of different constraints. The ones that are of interest in this parameter space come from the cosmic microwave background. So basically, if this dark photon exists, then photons in the cosmic microwave background would oscillate to the dark photons, thereby changing the spectrum. The reason why these constraints are weaker than you would naively expect is that typically there's an additional suppression factor that often comes in, which is once you're in a medium, the dark photon, there are some constraints that are in a medium, but there's an additional case, which is that the dark photon completely decouples if it has zero mass, because then you just have two massless U1s and you can redefine our photon as the one uniquely coupling to E and M, and then you just don't have a constraint, assuming, you know, you don't have another high scale measurement of alpha at the gut scale. This is exactly what you expect. So in the limit of the dark photon mass going to zero, all your constraints decouple as the mass of the dark photon squared. There's also some dependence on if you're doing a test in, for example, in a medium, which has a plasma mass, that's the relevant scale to compare to. If you're doing an experiment in a shielded environment where your metallic box is of a certain size, then that's the relevant scale to be comparing with. So there's some, how that decoupling happens depends on the specific search, but you can see all of these bounds are kind of going away as you go to the left-hand side. That's why these black hole systems, which are quite big, are interesting here, where the bounds are not very strong. Does it answer your question?
Definitely partially. I guess another thought was, I mean, are they not created in the Big Bang, but I guess they're behaving relativistically then, and so
yeah,
like
so these
photons,
are,
they don't. Go ahead.
yeah, so it depends. So these bounds, just assume these particles exist. There are stronger bounds if they are the dark matter, but it's actually surprisingly difficult to make these light dark photons the dark matter. People have tried very hard, and it's you keep running into various issues. So these are very weakly coupled. They could be produced from inflationary fluctuations, but these are too light for them to make up the dark matter. So in this region, they would be subdominant, and you don't produce enough of them through thermal interactions either. So basically, unless you build very multi-step models to create these particles, they're in this region of parameter space, they're not going to be the dark matter or have a significant cosmological abundance.
Yeah.
Thanks.
Which is why it's exciting that you can make them with black holes and then test them, because sometimes it's, yeah,
Well,
it can be
please
hard to get at them in another way.
right. Please excuse me again. I'm going to ask another question. You imply that the particles in this cloud are moving at relativistic speeds, and
The electrons are,
that they're
not
rotating. Yeah, excuse me.
not the particles. Yeah, the actual cloud is not moving relativistically.
Oh, not relative,
The
but
electrons inside the cloud get accelerated to relativistic speeds.
relativistic
The
speeds.
particles, the dark photons are
Yes.
sub-relativistic.
And what I was going to kind of not necessarily ask, but suggest even by a question is the Cherenkov radiation that comes from a relativistic particle radiation is an observable thing that comes from these. And if this cloud is rotating, okay, then you should be able to look with a telescope from one side of the black hole to the other and see the Doppler shift from these rotating Cherenkov radiation. That seems like a direct observable to me that would tend to be something that would validate your theories here, I should say.
Yeah, I mean, that's similar in spirit to what we're proposing. I'm not sure what you're picturing as radiating here. So the cloud itself is can't radiate because in photons, because these particles don't couple to photons in the way electrons couple to photons. But once you do have these charged particles, they do indeed lead to a lot of radiation, which is exactly what we're trying to observe. Yeah.
If any of these particles have electromagnetic charge,
yeah, they don't.
Then they radiate. Excuse
right.
me. They radiate, and like I said, and they radiate and if it's a rotating cloud, they radiate in one direction with a Doppler shift, and the other side of the cloud is rotating in the opposite direction. So they radiate also, and I'm talking about visible photons here, because I'm talking about the natural radiation that occurs from an electromagnetic particle. And so that's visible in terms of observations through a telescope. And it seems to me that that would be that the observation of such a Doppler shift from one side to the other from the radiating particles would be something that kind of validates your theory about how this is all working. Am I just dreaming or what? I mean, I don't know. And so I'm not suggesting that this observation has been made in the past, but I'm questioning, I'm suggesting that it be done in the future by astronomers or people that observe these things, because it has this implication, the implication that you're suggesting here of a rotating cloud of charged particles around the black hole.
Yeah, exactly. That's exactly my point. Thank you.
Oh, okay, well, no, I understand. That's what I meant. I hope somebody that's listening will pursue that.
Yeah, I definitely. Please tell all your astronomer friends that these are exciting signals to be looking for.
Okay,
That's the goal of this talk. So yeah, thank you.
I have a very
any other
limited
questions?
number of astronomer friends. Okay, so we'll see what we can do.
Great.
Any other questions from the attendees? Maybe I'll pose one myself. Excuse me for perhaps a question born of my ignorance in scales, but you said that you can have large occupation number for these particles, though they are ultralight. Is it never a concern that you have so many of them that you have to worry about perturbing the space-time around the black hole and no longer having it well described by like a pristine Kerr black hole that's just changing in spin, as opposed to a space-time that needs to be described by a black hole surrounded by an extended mass distribution?
Yeah, that's you're exactly right. So the I should have said these numbers and I forgot. So the amount of mass that is placed in this cloud can be up to a few percent of the black hole mass, but it is distributed over slightly bigger region. But as far as we know, these are some of the densest things that you can have around black holes. So these would be like really interesting objects to look for in the kinds of stuff you were mentioning at the beginning. So in terms of like how you actually get dense enough matter close to the black hole to perturb its metric, this is one of the best examples because the black hole generates it itself. When these calculations are done, especially by folks like Will, East, and Nils, they do the full thing, or some of them, the calculations take into account the full back reaction on the metric. So the main back reaction is, of course, that the black hole is spinning down, which you can kind of easily see just from angular momentum conservation and see analytically. And then you have a perturbed, you also have a perturbed metric, which gives you corrections to the energy of the particles, for example. So you have a self-gravitational energy of the particle, which is what's actually giving you this positive F dot drift, which is quite interesting. Because that self energy is changing over time. So yeah, exactly. And we did spend some time thinking about like, can you see these? In principle, you can, if these are in a merger and they survive up until the end of the merger, you might be able to see the effects of perturbing the Kerr metric. But it seems like the parameter space for that is fairly small. I think Mina's thought about this more recently, but yeah,
there was a student that worked this out over the summer for several regimes. Unfortunately, as Masha said, the numbers, at first we thought it was going to be a big effect, but for mergers, binaries, but it looks like if you take into account non-distributions, blah, 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 looks like you have to be, even if you're super optimistic, it's highly unlikely. You have to be really lucky. I mean, we cannot, it's probabilities that were estimated, but unless you win the lottery, it doesn't look like. But F dot is, as Masha said, is something that is very unique to this, and it is the back reaction that does this.
Excellent. And are there any more questions? All right, maybe I'll pose one more and then I'll close it out. And perhaps you already said this, and I'm sorry if I missed it, but can you tell me for these new types of pulsars, it's nice that they have this kind of possibility periodic signal, but are they as long-lived as traditional pulsar signals, or do they eventually cut off at some time scale that you could catch it over several cycles, but eventually it would die if you were to observe it for years?
Yeah. Great. So yeah, I think this is what I was kind of skipped at then because I was running out of time. So the signal period scales as 1 over the mass of the particle. Then the growth time of the signal scales as, this is set by the gravitational interactions, scales as this alpha parameter, which is less than 1 to 6 power times the mass of the particle. And then the decay time is alpha to the 12th. So for example, you could have signals that rise over hours and fall off over months. Or for a smaller alpha, you could have signals that rise over years and fall off over thousands of years. So those are the kind of 2 classes of searches that we're thinking about. If it's a large alpha, so strong gravitational coupling of the particle, these are good for like fast follow-ups. So you see a merger and then you follow it up that same day or within a month. And then you can also actually see it decay over time with a very specific envelope, right? So you can correlate the fact that there's a pulsation at a specific period. You can correlate that to the rise time and the fall off time. Or if the coupling is weaker, then you can look at these blind searches or these pulsars, which have been around for thousands of years and are like slowly spinning up because of the emptying of the cloud.
Excellent. So
Excuse
let
me,
me just.
I want to make a comment about what you've asked just now. And that is, it's got to do with what I'll call the metric around the black hole. And my understanding of this, and as best as I can figure out, is that these decay times, the space-time around a black hole is distorted because of the metric, and the degree of distortion depends on the mass of the black hole. And so I'm not really clear that I think that that's the important factor in regard to the timescales that are involved here, because space-time is what the metric is all about. And it's more distorted with that.
So the ratio, this alpha is actually, I might have skipped over it a bit, but this is actually the ratio of the black hole size to the Compton wavelength of the particle. So that the black hole mass is kind of implicitly hiding in this strength of the gravitational attraction between the black hole and the particle. So that is, you could rewrite this all as scaling as the black hole mass rather than the particle mass.
Except I see, of course, in your equations there that the how can I say, these signal times are inversely proportional to quite a substantial power of A, and so that's what I mean. That it seems to me that the black hole mass is the more effective parameter rather than the mass of the particles in regard to these time scales. And so since we have a lot of different masses of black holes, there are going to be a lot of variety in these scaling factors from one black hole to another. Just looking at it and thinking those thoughts. So that's all I have. Thank you very much for listening to me.
Thanks for your questions.
All right, everyone. Thank you so much for coming.
Thank you.
Once again, Mina and Masha, I cannot thank you all enough for a very exciting talk and discussion. Thanks for those of you who attended. We'll have another seminar for you all in a month. So see you then, and tell your colleagues to tune in as well.
Thanks for sticking around in the questions. Nice to meet you.
Bye.
Okay, nice to meet you all too. I was wondering